Look up, just look up. Every tiny dot of light in that canvas above you is a star, a fusion engine burning silently across unfathomable distances. But what makes it burn? What keeps that light going for billions of years without wires, batteries, or fuel trucks? That is the question that haunted scientists for centuries. Because you see, for the longest time, we had no idea. Even the greatest minds of their time, Newton, Kelvin, guessed that the sun might be burning coal. It made sense back then. Fire needs fuel, and when fuel runs out, the fire dies. But there was a problem. Coal couldn't keep a star burning for billions of years. It would run out in just a few thousand. Yet the sun had been shining long before humans ever looked up. So clearly, it wasn't burning wood, or coal, or even magic. Something much deeper, much more powerful was at work. And the secret, as it turned out, was hidden in the very heart of matter. Let's begin with the simplest atom in the universe, hydrogen. Just one proton, one tiny piece of an atomic puzzle. But under the crushing weight of a star's gravity, hydrogen atoms are forced closer and closer until something unimaginable happens. They fuse, they become one. This process, nuclear fusion, is the true flame of the stars. It's not a chemical reaction like burning paper. It's a nuclear one, where the very cores of atoms merge. And when they do, they release energy, a lot of it. More energy than we can produce in any power plant. More than all the bombs ever built. All from a few atoms and a little pressure inside stars. This fusion happens continuously. Every second, our sun fuses around 600 million tons of hydrogen into helium. And in doing so, it converts a small fraction of mass into pure energy. Einstein explained this with the famous equation, E equals mc, energy equals mass, multiplied by the speed of light, squared. That c is huge. And when you square it, even a tiny amount of mass becomes a colossal amount of energy. That's the energy you feel when the sun touches your skin. That's the fire lighting every distant star. So why do stars shine? Because their very atoms are collapsing, fusing, and releasing the universe's purest form of energy. Because gravity squeezes hydrogen into something hotter than fire, something older than time, a slow, gentle apocalypse that looks like a twinkle from 93 million miles away. And the most beautiful part, they do it quietly, gracefully, for billions of years, without asking for anything in return. That's why stars shine, because the universe decided to light itself from within. Let's dive deeper. Inside the core of every star, there is no silence, there is no stillness, there is only the ancient, ongoing dance of atoms. You see, stars are not just hot, they are unimaginably dense at the core, billions of tons pressing inward per square inch. The temperature, over 15 million degrees Celsius. At this point, matter stops behaving normally. It becomes plasma, a sea of charged particles, protons, electrons, nuclei, all swirling, all colliding. And this is where fusion happens. But it doesn't happen easily. You see, protons, the positively charged particles inside hydrogen atoms, don't like getting close. Like two magnets facing the wrong way, they repel. But gravity is patient, and heat is persistent. Eventually, two protons are smashed together with enough force to overcome their mutual hatred. And in that single, rare moment, they fuse. This begins what's called the proton-proton chain. It goes something like this. Step 1. Two protons collide. One turns into a neutron. Together, they form deuterium, a heavier form of hydrogen. Step 2. Deuterium meets another proton. They form helium-3. Energy is released in the form of gamma rays and neutrinos, tiny ghost-like particles that fly straight through matter, including you. Step 3. To helium-3, nuclei meet. They fuse into helium-4 and release 2 more protons back into the soup. That's it. That's the dance. 3 steps, infinite repetition, millions of times per second, in every single cubic meter of stellar core. This is how stars burn, not with fire, but with fusion, not with chaos, but with choreography. Now, in stars heavier than the sun, there's an alternate route called the CNO cycle. Here, carbon, nitrogen, and oxygen act as catalysts, helping protons fuse into helium while staying unchanged themselves. It's faster, more complex, but the result is the same. Helium, light, heat, life. Fusion is not just power, it's poetry in motion. It's the cosmic heartbeat that pulses through the night sky, and it's happening right now. In the stars you can see, and in the stars you can't. Every flicker, every glow is a whisper from deep within, telling you that atoms are dancing, that matter is learning to shine. So sleep well tonight, knowing that in the heart of darkness there is always light. There is always fusion. There is always the waltz. Gravity wants to crush the star, but fusion pushes back. It's a cosmic arm wrestle, and they're perfectly matched. In the core, fusion happens. In the radiative zone, energy travels outward, slowly, like light lost in a fog. It takes thousands of years to escape. Then comes the convective zone, where hot gases rise and cool gases sink, like a stellar soup stirring itself. This balance between pressure and collapse is what keeps a star alive. Not too fast, not too slow, just equilibrium. Stars are not wild, they are balanced. They may look like chaos, flames, flares, explosions, but inside there is order, a deep and ancient order between 2 forces, gravity and heat. Let's begin with gravity. Gravity is the silent sculptor. It shapes clouds of gas into spheres. It crushes atoms together. It begins the fusion. But gravity is greedy. It always pulls inward. If left alone, it would crush the star into a tiny, dark speck, a ghost of its former self. So what stops it? Heat. Not the kind from a campfire, not even from lava, but something far more intense. Something born of fusion. Every time 2 protons fuse, a small flash of energy is released. That energy creates pressure, an outward force that pushes back against gravity. This balance is known as hydrostatic equilibrium. In the core of the star, fusion generates heat. That heat creates pressure. The pressure pushes outward. Gravity pulls inward, and the 2 cancel out perfectly for billions of years, like a breath that never ends. But this heat doesn't stay in the core. It travels outward, slowly, very slowly. The first region it enters is called the radiative zone. Here, energy moves as photons, tiny packets of light, but their journey isn't easy. Photons bounce, scatter, absorb, re-emit billions of times, like being stuck in cosmic traffic. It can take 100,000 years for a single photon to travel from the core to the surface. Just imagine the sunlight hitting your skin today. Might have been born when humans first painted caves, and then comes the convective zone, the outer layer, where energy moves not as light, but as movement. Hot plasma rises. Cool plasma sinks, like a simmering pot of starlight. These swirling currents carry energy the rest of the way to the star's surface. And from there, into space. That's the light you see. That's the warmth you feel. The story of a photon's journey from the crushing center of a star to the quiet of your bedroom window. It's strange, isn't it? The star doesn't explode. It doesn't collapse. It simply exists, perfectly balanced between the weight of gravity and the whisper of heat. It breathes, it glows, it endures. So next time you feel warmth on your face, know that you're standing in the middle of a very old argument between gravity and light. And for now, light is winning. But no dance lasts forever. When hydrogen runs out, the core contracts, the outer layers swell. The star becomes a red giant. Now it starts fusing helium, then carbon, then oxygen, layer by layer, like a cosmic onion, until it reaches iron. And iron is the full stop, because fusing iron doesn't give energy. It takes it, and without pressure, gravity finally wins. The core collapses. In some stars, it's gentle. They become white dwarfs. In others, it's dramatic. They explode. A supernova, the loudest goodbye in the universe. Everything ages, even stars. They seem so eternal, don't they? Steady, glowing, timeless. But they too grow old. Stars are born from clouds of dust and gas, shaped by gravity into a sphere, ignited by heat and pressure into a blaze of fusion. But no fire burns forever, you see. A star spends most of its life in what's called the main sequence, the long, stable middle chapter of its life, burning hydrogen into helium at a steady pace. Our sun is there now, calm, balanced, glowing, but deep inside, with every passing second, hydrogen becomes helium. And that helium builds up in the core, like ashes in a fire. Eventually, there's no hydrogen left in the center to burn. And that's when the star begins to change. It begins to grow old. As the core runs out of fuel, it contracts under gravity. It grows hotter. It compresses. Meanwhile, the outer layers, freed from the balancing heat, begin to expand, swell, bloom. The star becomes a red giant. Imagine it, our sun one day, so large that it swallows Mercury, then Venus, then perhaps even Earth. But this swelling isn't death, not yet. It's transition. Inside that massive, aging furnace, helium atoms begin to fuse into carbon, then carbon into oxygen, then into neon, then magnesium, silicon. Each new element formed in a shell surrounding the core, layer upon layer, like the rings of a cosmic onion. But there is a limit. Eventually, the core forms iron, and here, the process stops, because fusing iron doesn't release energy. It absorbs it, and without energy, there is no pressure, no outward force, no balance. Gravity, always patient, finally wins. And what happens next depends on the size of the star. If the star is small, like our sun, it shrinks into a white dwarf, a dense, hot, Earth-sized ember. No more fusion, no more fuel, just glowing memory. It may fade over trillions of years, eventually becoming a black dwarf, cold, dark, invisible. But if the star is massive, more than 8 times the mass of the sun, then the collapse is far more dramatic. The core implodes. In less than a second, the inner layers crush down and then rebound outward in a colossal supernova, one of the most violent events in the cosmos, brighter than an entire galaxy, hotter than the core of creation itself. In this moment of destruction, elements are born, heavy ones, like gold, uranium, platinum. This final act of death is also an act of creation. The star dies, but its ingredients are scattered across the galaxy to become part of new stars, new planets, and eventually new life. The star becomes a legacy. This is the cycle: birth, life, expansion, collapse, rebirth, not in the same star, but in the universe as a whole. You see, the calcium in your bones, the iron in your blood, the oxygen you breathe, was all formed inside a dying star. You are not just looking at starlight, you are starlight. So when you think about growing old, about change, about endings, remember the stars. They to change, they to end, and in their ending, they leave behind the very building blocks of everything we know. Their death is our beginning. In that final breath, the star becomes a forge. In the extreme pressure and heat of a supernova, new elements are born: gold, silver, platinum, uranium. These aren't from Earth. They are born in death, the last sigh of a star. So when you wear a gold ring, you're wearing the ashes of a supernova. Everything heavy in your body, iron in your blood, calcium in your bones, it came from this chaos. We are not just observers of the stars. We are their children. In the final breath of a massive star, as fusion halts, as iron chokes the core, something ancient awakens. Collapse, not gentle, not slow, but sudden, violent. The core folds in on itself, crushed by gravity. Atoms shattered. Protons and electrons merge into neutrons. A city-sized sphere of pure neutron matter is born in less than a second. Outside the core, the star doesn't go quietly. It roars. The outer layers rebound off the collapsing center, ripping through space in a supernova. A cosmic scream louder than anything you've ever imagined, though you'd never hear it. Space is silent, and yet its light can outshine an entire galaxy. Just for a moment. This is not death, it is metamorphosis. The remains of that implosion may become something strange, something dense, something no earthly matter compares to: a neutron star. Imagine compressing the sun into the size of a city, about 20 kilometers wide. A teaspoon of it would weigh 1 billion tons. That's a neutron star. They spin fast, sometimes hundreds of times per second. Some send out beams of radiation, like lighthouses of the galaxy. We call them pulsars. Each tick you hear could be a star, spinning 700 times per second, from thousands of light years away. But this is not the end of extremes. There is something deeper. If the star was massive enough, too massive for even neutron degeneracy to resist, then nothing can stop the collapse. Nothing. Gravity wins entirely. The core disappears into itself, falling forever, not compressed, but erased from space and time. This is a black hole. It is not a thing. It is not an object. It is a region, a point beyond which nothing can return. Not light, not time, not even information. We call it the event horizon, the edge of knowability. Beyond that, we can't see, we can't know, only imagine. It's not a hole, but a distortion of reality itself, where time slows, where gravity stretches, where the very laws of physics tremble. Some black holes spin, some are still, some eat matter, pulling stars apart like spaghetti, an actual phenomenon called spaghettification. Elegant name, terrifying concept. They sit at the centers of galaxies, sleeping, waiting, growing. One sits at the heart of our galaxy, Sagittarius A*, a supermassive black hole, millions of times the mass of our sun, and yet invisible. We only know it's there because of how stars dance around it, curved by its unseen gravity, like leaves circling a silent drain. So what happens inside? Truth is, we don't know. The equations break. Physics collapses into paradox. Some believe the core becomes a singularity, a point of infinite density, where time ends, where space ends. Others suspect something stranger, that black holes may connect to other places, other universes, through wormholes. But for now, all we have is speculation. A black hole is not evil, not dangerous from afar, not hungry. It is simply the logical conclusion of mass and gravity pushed too far. It is nature taking itself to the very edge. And what's more poetic, from the death of a star comes the birth of mystery. We are drawn to these things, these dark places in the cosmos, not just out of fear, but out of wonder. Because what lies beyond the event horizon may be the final frontier, and maybe, just maybe, one day we'll cross it. No telescopes could see inside a star. So how did we know? With brilliance, with math, with curiosity. Cecilia Payne discovered that stars are made of hydrogen. Hans Bethe explained the fusion reactions in the sun. Fred Hoyle predicted how carbon forms. Chandrasekhar found the mass limit before a star becomes a black hole. These were stargazers of the mind. They didn't just look at the stars. They understood them, and so can you. Even if your eyes are closed right now, when the universe was born, it was simple. Just hydrogen, some helium, and a whisper of lithium. No oxygen, no carbon, no iron, no gold, no planets, no life, no us. The universe began as pure potential, an ocean of simplicity waiting to become complex. But the stars, they were the alchemists. Inside their cores, fusion began. Hydrogen into helium, helium into carbon, carbon into neon, neon into oxygen, oxygen into silicon, silicon into iron. Like climbing a nuclear ladder, each step a little heavier, a little hotter, a little faster. Each atom forged from the pressure of millions of tons per second. Each element a cosmic invention. And just when a star had given everything it could, when it had created iron, the element it cannot burn, it died. But it did not die quietly. It exploded. A supernova. In that chaos, in that unimaginable heat, the universe did something bold. It created everything else. Gold, platinum, uranium, nickel, cobalt, iodine, lead. These were not made in life, but in death, the death of stars. The same explosions that destroy stars also scatter their pieces into space, into clouds, into gas, into future solar systems, into you, the calcium in your bones, the iron in your blood, the oxygen you breathe, the carbon in every part of your being. It all came from stars. You are not made of stardust. You are stardust. And that is not poetry. That is physics. Let's go deeper. Some elements were made, even later, in the collision of neutron stars. A dance of two city-sized corpses spiraling together, crashing, and in that final moment, they release energy so intense they forge gold. Yes, that ring on your finger. It might have come from the death spiral of a binary neutron star 1 billion years ago. Wrapped around your skin is the history of the cosmos. Stars died so planets could live. Their ashes became worlds. And on one of those worlds, in a quiet corner of a spiral galaxy, a species of stardust became self-aware. We are atoms. contemplating atoms. We are made of the stars, and now we study them. The forges of the cosmos, the origin of every bite you eat, every breath you take, every heartbeat you feel. In the language of science, there is a phrase for this process: stellar nucleosynthesis. But to your soul, it may sound more like destiny. The stars built the universe, and now they live inside you. We've watched stars long enough. Now we want to make one. In labs like ITER in France, we are trying to recreate fusion on Earth. It's not easy. You need 100 million degrees. You need to trap plasma in magnetic fields. You need patience, precision, perseverance. But if we succeed, we'll have infinite clean energy, just like the sun. And maybe we'll finally bring starlight down to Earth for billions of years. Stars have burned, not with fire, but with fusion. And now we are trying to do the same, to capture the fire of the stars in a bottle. Not to worship the sun from a distance, but to recreate it right here on Earth. Fusion. The process of taking light atoms, hydrogen, deuterium, tritium, and forcing them together until they become helium. Releasing titanic energy in the process. Not splitting atoms like fission, but fusing them. No radiation nightmares, no meltdowns, no long-lived waste, just power. As clean as the stars, as pure as sunlight, as infinite as hydrogen itself. Right now, across the world, scientists are working in silence to make fusion real. In France, the ITER project builds a tokamak, a device shaped like a giant metallic donut, designed to trap plasma in magnetic fields hotter than the core of the sun. In the US, at the National Ignition Facility, 192 lasers focus on a tiny pellet of hydrogen, hoping to ignite a fusion flame. In China, Germany, the UK, quiet revolutions are underway. Because if we succeed, we will never need coal, never need oil, never burn the earth again. Imagine a world where the only byproduct of energy is helium, where a cup of seawater could power your city for a week, where deserts bloom with light and factories hum cleanly into the night, where war over oil becomes a ghost of the past, because we found something better, because we dared to unlock the fire of the cosmos, because we remembered that we, too, are made of stars. Fire was the first gift. Prometheus stole it from the gods. It warmed our caves, cooked our food, lit our path through the darkness. But fusion is not just fire. It is the source of fire. It is the script of stars written in atomic light. And maybe, just maybe, the story of the universe was always leading to this moment, where stars birthed life, and life looked back and said, "Let us burn as they burn. Let us fuse. Let us become what we were always meant to be, not just stardust, but starlight." Let's take a moment, breathe in, let the air move slowly through you. Now exhale, let go. You're here now, listening, floating through thought. Let me tell you something beautiful. There is a reason we stare at fire, a reason the sun entrances us, a reason candlelight makes us feel safe. It's not just warmth, not just survival, it's memory, encoded in your DNA, in your skin, in your heartbeat, because every atom in your body was forged in fire. Not earthly fire, but stellar fire, supernova fire, thermonuclear fire. And that fire, that force, that cosmic breath is what we now seek to understand, to tame, to replicate. We are not just building reactors. We are attempting something sacred. We are rewriting nature's most intimate poetry with mathematics. At the heart of every fusion reactor is a storm, a sun-sized tantrum, spinning plasma, reaching temperatures so absurd they no longer make emotional sense. 150 million degrees Celsius. Think about that. It's not heat you feel, it's heat that melts meaning. At that point, hydrogen forgets itself. It no longer knows it's a gas. It becomes plasma, a state so energetic it hums in magnetic suspension, levitating, contained only by invisible threads of math, magnetic bottles, spinning rings, confinement not by walls, but by rules of the universe. Do you understand how delicate that is? The star we build must never touch the walls that contain it, because those walls will melt instantly, like ice before lightning. So we balance it, a dancing flame held in place by invisible fields. We do not tame the sun, we negotiate with it. Now imagine, this star we hold is no bigger than a grapefruit, yet it consumes more electricity than a small city. Why? Because we are not yet gods. We are learning, still in the nursery of nuclear alchemy. But someday, we will light that flame not for 2 seconds, but for hours, days, years, forever. And when we do, the game changes. Because fusion doesn't run on oil. It doesn't need uranium. It feeds on hydrogen, the most abundant element in the universe. The same stuff in water, in your blood, in the stars. 1 glass of seawater holds enough fusion fuel to power your home for centuries. We're talking about abundance in an age of scarcity, about infinite clean energy in an age obsessed with limits. And yet, we move slowly, not because we lack intelligence, but because we respect the magnitude of what we're doing. After all, we are not building power plants. We are building stars on Earth in steel shells, held by magnets, monitored by minds that still fear the dark. And with every step closer, we ask, what will the world look like when energy is no longer a problem? What happens when every village, every city, every home can pull power from the same process that lights up Andromeda? What happens when fusion becomes freedom? Think about war, about hunger, about climate collapse. So many of these are stories about energy. Who has it? Who doesn't? Who controls the tap? Who gets to dream at night? And who lives by candlelight? But with fusion, there are no barrels, no borders, no pipelines, no monopolies, just the universal recipe that every star already follows. And here's the most miraculous thing. We didn't invent fusion. We remembered it. We decoded what nature has done effortlessly. For billions of years, we reversed the ancient silence of stars and made it speak in equations, in engineering, in experimental fire. Let me say this plainly. The future does not run on batteries. It runs on stars. Artificial, human-made, engineered, but stars nonetheless. And if we get it right, then your children will never know what it meant to fear a blackout, to measure progress by how much oil a nation owns. Instead, they'll grow up with suns in every continent, silent, humming cores of endless warmth that ask for nothing in return but understanding. Let me tell you a secret. The universe is not cold. It is brimming with energy, waiting for us to learn how to speak its dialect. That dialect is fusion, soft, relentless, fair. It gives more than it takes. It builds without destroying. It sustains without polluting. If we had begun earlier, the oceans would be cleaner, the skies clearer, the glaciers thicker. But regret does not power tomorrow. Curiosity does. And in labs across the world, curiosity burns brighter than ever. We are close, closer than ever before, not to making a machine, but to whispering to the universe. We understand. Teach us how to glow, because maybe, just maybe, the next big leap for humanity won't be another skyscraper or spaceship or smartphone. It will be a room where plasma dances without fear, a sun wrapped in wire, spinning calmly at the heart of our civilization. That's the dream. That's the work. Not science fiction, not fantasy, just humans doing what stars do. And so, as the stars continue to burn, as galaxies drift like lullabies across space, we'll leave you here, in silence, in stardust, in thought. This has been CortexFlare, where we turn the universe into a bedtime story, and science into a quiet companion for the curious, the tired, and the dreamers. If your mind is still spinning, or your eyes just softly closed, either way, you're exactly where you need to be. Sleep well, or wonder more. We'll be back with the next cosmic thought. Good night, fellow stardust. See you among the nebulae.